How are you, student? Welcome to Manifested e-learning platform. My name is Purity Anzelimo, and our subject today is physics, and our topic is waves. And that is waves 1 in form 2. Waves 1, we are going to continue. We have covered a lot in waves 1, and we can do a recap of what we covered during our previous lesson, where we looked at the terms associated with waves, and we looked at the following. 1, amplitude, denoted by a capital letter A, and we say that amplitude is the maximum displacement from the mean position. Then we had another term, that is frequency, denoted by a small letter f. And what did we say is frequency? Frequency simply refers to the number of complete oscillations in 1 second. That's what we mean by frequency. And the SI unit for frequency is hertz. Then we went ahead and looked at periodic time, denoted by a capital letter T. And we say that periodic time simply refers to the time taken to complete one oscillation, or time for one complete oscillation. Then finally, we looked at another term, that is wavelength. Wavelength is denoted by a Greek letter lambda. That is it. And we say we can define wavelength in so many ways. For example, we can say wavelength is the distance between two successful crests, or we can say it is the distance between two successful troughs, or we can say that it is the distance between 2 points which are in phase. So that is on wavelength, and we say that the SI unit for wavelength, being a length, is meters. And therefore that will usher us into what we are going to discuss during our lesson today. We are going to look at what we refer to as speed. Speed is denoted by letter V. Speed and velocity denoted by letter V. So we are going to look at speed in our lesson. Then we are also going to look at the relationship that exists between frequency, wavelength, and speed. We look at this relationship, and then from this relationship, then we'll be able to solve some numerical problems. So by the end of this lesson, you should be in a position to define speed. You should also be in a position to derive this equation that will relate frequency, wavelength, and speed, and also apply it in numerical problems. Now, we start with the definition of speed. Now, this is not a new term. You learned it also in Form 1, in mathematics also. What is speed? Now, when we talk of speed, and here we are talking of the speed of a wave. So when we talk of speed, it simply refers to the distance covered by a wave in 1 second. Because we define speed in mathematics as distance covered per unit time. So in waves, we are just going to use the same definition and say that speed refers to that 1 second is now the unit time. So it is the distance covered by a wave in 1 second. And from this definition, therefore, we can be able to get the SI unit of speed, because we are saying that speed is distance divided by time, and therefore our SI unit, the SI unit for speed, will now be meters per second. So the SI unit is meters per second, which we write as meters per second, or simply meters per second is that. So that is the SI unit for speed. So that is speed of a wave, distance covered by a wave in 1 second. So I want us to move ahead and look at the relationship that exists between frequency, wavelength, and the speed of a wave. So let's look at the relationship. Relationship between speed, wavelength, and the frequency. Remember, we are in waves, so we are talking about the speed of a wave, the wavelength of a wave, and then the frequency of a wave. And here we are going to consider that the period of a wave is t. So suppose t for periodic time, and then the distance covered in time t is lambda. So that is what we are going to consider when we want now to come up with an equation that we are going to use in solving numerical problems. So we suppose that the period of a wave is t. We say that periodic time is the time taken to complete one oscillation, and then the distance covered in that time t is lambda, which is the wavelength. So we want now to relate and see. And therefore from this, we can be able to say that therefore the speed of that wave, from that information, the speed v will therefore be equal to the distance covered, and the distance covered in our case is lambda, all over the time taken. And the time here is t, the periodic time. So from this, now that we know speed is distance covered per unit time, so we have that our speed, v, is distance all over the time taken. And therefore from this, we can say that the speed will be equal to wavelength divided by the periodic time. Make note of this. So the speed will be equal to the distance, which is the wavelength, divided by t, which is the periodic time. But when we were defining these terms, frequency and periodic time, we realized that there is a relationship between the two, whereby we say that frequency is the reciprocal of the periodic time, and the periodic time is the reciprocal of frequency. And therefore, in our denominator here, which is the periodic time, we can come and say, but periodic time is the reciprocal of the frequency. And therefore, from this, we can say, therefore, that our speed will be equal to wavelength divided by periodic time, where our periodic time is 1 over f. And therefore from this we can say that our wavelength all over 1 over f means it is the same as wavelength divided by 1 over f, which is the same as wavelength multiplied by f over 1, which is equal to lambda f. And therefore we can come and make a conclusion here. From that, therefore, we can say that the speed is equal to frequency multiplied by wavelength. Remember, multiplication is commutative, so it doesn't matter when we talk of 1 times 2 or 2 times 1 is the same. So we can start with frequency multiplied by the wavelength. And this is the relationship that exists between the speed, frequency, and the wavelength. And this equation is referred to as the wave equation. This is the wave equation. It applies for all the waves. It is the wave equation whereby speed is equal to frequency multiplied by wavelength. So we can say where can define these terms where V is the speed of the wave, and we say that it is in meters per second. Then our F is the frequency, and the frequency is in hertz. And then we have our lambda, which is now the wavelength, and the wavelength is in meters. So whenever you are applying this equation, ensure that every quantity is in its SI unit. The SI unit for speed, for frequency, and for wavelength. So this is what we are calling the wave equation. Hoping that that is clear. We are going to apply this in solving some problems. But before we get to that, I would like you to note the following from our wave equation. From that wave equation, whereby the speed is equal to frequency multiplied by the wavelength, if we make frequency the subject of the formula, then it will mean that F will be equal to V all over the wavelength, meaning that frequency and wavelength are inversely proportional. As you can see, they are inversely proportional. An increase in the frequency will lead to a decrease in the wavelength, because the speed of the wave in a given medium is constant. So if this is constant, then it means that if the frequency increases, then it means that the wavelength will decrease, and vice versa. And therefore we can have a plot of a graph. We can have a plot of a graph of frequency against wavelength. A graph of frequency against wavelength, and we are going to have it as follows, since we are saying that the two are inversely proportional. So this is the plot that we are going to have. On this side we have our frequency in hertz. Then on the x-axis we have wavelength in meters. So we are saying an increase in one will lead to a decrease in the other, and therefore we are going to have our curve like this. So that is the plot for frequency against wavelength. You can see, if for example at this point here, at this point, we can check and see what's happening as the wavelength increases. So you can see when the wavelength is at this point here, you can observe and see how the frequency is. And as the wavelength increases, if at this point we come and check at this point here, as the wavelength increases, what happens to the frequency? It's clear from here. So you can see, initially when the wavelength is low, the frequency is high. And when the wavelength is high, the frequency is low. So that is what we have as the relationship between frequency and wavelength. I would like you to note the following. Note down the following. NP, we are saying that the rate of vibration of the vibrator or the source determines the frequency of the waves. That is key. The rate of vibration of the source determines the frequency of the wave. We say that frequency is the number of oscillations in 1 second. So the rate of vibration, the more the vibrations, the more the frequency of that wave. And then we say that also the speed of a wave in a given medium is constant. So if we are using, or if it is a wave, maybe a water wave, the medium is water. If the speed at the beginning, we are talking of 40 centimeters per second, that speed is constant because it is in a given medium. So you need also to make note of that. So the rate of vibration of the source determines the frequency of the wave. So the more the vibration, the higher the frequency of the wave. Then the speed of a wave in a given medium is constant. So I want us, having now been able to derive the wave equation and having noted the following, we now want to solve some numerical problems involving our wave equation. Our wave equation, V is equal to F multiplied by lambda. So from that equation, we can be able to calculate any of the quantities. We can even have a triangle whereby we can relate the three. We know that this one, the vertical one means multiplication and the horizontal line means division. So we can come and say therefore that our V is equal to frequency multiplied by wavelength. So from this it's very clear that when we want to get the speed, it is simply frequency multiplied by the wavelength. When you want to get the frequency, it's simply the speed divided by the wavelength. And when you want to get the wavelength, you take speed, you divide by the frequency. So we want to apply it in some numerical questions. So that's the question that we have been given. We can read it. We are told that a radio wave has a frequency of 3 megahertz and travels with a velocity of 3 times 10 power 8 meters per second. What is its wavelength? So that's the question. So the first thing we need to do is to analyze and see the quantities given and what is in question. So we are told that the radio wave has a frequency of 3 megahertz. So the frequency is given as 3 megahertz. We are also told that the velocity of the wave, so the speed of this wave is 3 times 10 power 8 meters per second. Remember, we use velocity or speed. These two are the same, only that for velocity, it is a vector quantity. It has both size and direction, whereas for speed, it has only the magnitude or the size. So we have the velocity or the speed of that wave as 3 times 10 power 8 meters per second. What is its wavelength? So what is in question is the wavelength. So before we get to calculate the wavelength, we need to ask ourselves, is frequency in its SI unit? Is velocity in its SI unit? So if you look at the frequency, it is in megahertz. And remember, we said that the unit for frequency is hertz. So how many hertz make 1 megahertz? We need to note that 1,000,000 hertz is an equivalent of 1 megahertz. And therefore, we can convert 3 megahertz into hertz. So we are going to have 3 times 1,000,000 over 1. 3 times 1,000,000 all over 1. So we end up getting 3 million hertz. So the frequency is 3 million. Then we ask ourselves, is the velocity in its SI unit? Yes, in meters per second. And therefore, we just come and apply the wave equation. So the wave equation, V, is equal to wavelength multiplied by the frequency. So our V is 3 times 10 power 8 is equal to wavelength, which is in question, multiplied by the frequency, which is 3 million hertz. I can just leave it that way, 3 million hertz. So we are going to have this 3 times 10 power 8 is the same as 3 times 1, 2, 3, 4, 5, 6, 7, 8, which is the same as 300 million is equal to 3 million multiplied by the wavelength. So for us to get the wavelength, we can divide both sides by 3 million. This other side by 3 million. So this one will cancel. These 6 zeros will cancel. And by 3, 1 by 3, 1. So we end up getting our wavelength is 100. And therefore we can come and say that wavelength will be 100, and the unit for wavelength is meters, because all the other units are in their, all the other quantities are in their SI units, and therefore our wavelength will be 100 meters. Is it okay? So that is what we have. We have applied the wave equation and we have solved the wavelength which is in question. So we want to move ahead and do another example. So that is what we have. We have Roman 1. We'll also solve Roman 2 and 3. So in this we are told that waves on a spring are produced at the rate of 20 wavelengths every 5 seconds. So we are told to find the frequency of the wave motion. Now here we are having 20 wavelengths. Now when we talk of 20 wavelengths, remember we said when we are talking of a wavelength, for example, if it is for a transverse wave, we have it, if we are beginning from here, we have the crest and the trough. That is one wavelength. Then if we continue and continue, so we are having 20 wavelengths, meaning that 20 wavelengths is an equivalent of 20 complete oscillations, because one wavelength is an equivalent of one oscillation. So we are told to find the frequency of the wave motion. And we know that frequency refers to the number of oscillations in 1 second. Number of oscillations in 1 second. So we have 20 oscillations. These are 20 oscillations and they are in 5 seconds. So we want to know, what about in 1 second? How many oscillations will we have? That will be the frequency. So we have 20 times 1 all over 5. So we have 20 times 1 divided by 5. 20 divided by 5 is 4. And therefore our frequency is 4 hertz. Because frequency is the number of oscillations in 1 second. And we have 20 oscillations in 5 seconds. So that becomes our frequency. So we move on to Roman 2. So that's part 2. We are told if the wavelength of the waves is 0.01 meters, find the speed of the waves. We have been given the wavelength and we have been told to find the speed of the waves. So how do we go about it? Remember in the first part we had calculated the frequency. So we already have the frequency as 4 hertz. Then we are told that the wavelength is 0.01. So lambda is 0.01 meters. So we are told to find the speed V. So here we again apply the wave equation, whereby the speed will be frequency multiplied by the wavelength. The frequency is 4, the wavelength is 0.01, and therefore we end up getting 0.04. It is the speed, which is in meters per second. So that is the velocity, or what we are calling the speed of the waves. So when you have this, you can simply apply the wave equation. Finally, in that question, Roman 3, so part 3, you are told to find the period of the waves. So remember, when we talk of period, it simply refers to the time taken to complete one oscillation. So we can apply two different methods. Again, we know that period is the reciprocal of frequency. We can start with that one. We want to find the period T, and we have the frequency. We calculated the frequency to be 4 Hertz, and we know that periodic time is the reciprocal of frequency, and therefore the periodic time T is 1 over frequency, which is 4. So 1 over 4 is the same as, when you use your calculator, that's a quarter, so it's the same as 0.25, and it is periodic time, so it is 0.25 seconds. That is the period. Alternatively, we can say the following. Alternatively, we can, from the definition of period as the time, periodic time as the time for one oscillation, we can just come and say we have 20 oscillations in 5 seconds. We have 20 oscillations in 5 seconds. So we want to know what is the time for one oscillation. So what about one oscillation will be in how many seconds? Because that is the periodic time. So we just come and cross multiply 1 times 5 divided by 20. All over 20, which is 5 over 20. 5 over 20 is the same as 1 over 4, which is the same as 0.25 Hertz. Sorry, not Hertz. 0.25, that is the periodic time, and therefore it's in seconds. So you can approach it in this way or in the other one where we have used the formula. So hoping that you are now able to apply the wave equation to solve various numerical problems. When you are given a question, always remember we've seen that V is equal to frequency multiplied by the wavelength. And you must ensure that all the units, all the quantities are in their SI units. So I'd like to give you a question. So an exercise for you to work out. So here is the question. Water ripples are caused to travel across the surface of a shallow tank by means of a straight vibrator. The distance between successful crest is 3.0 centimeters. So you need to note something about that distance, the distance between successful crest. We say that the distance between two successful crests is the wavelength. So it is 3.0 centimeters, and the waves travel 25.2 centimeters in 1.25 seconds. So you are told to calculate the wavelength and the velocity of the wave, and finally the frequency of the vibrator. So ensure that you go through the question and work it out. So in our next lesson, we'll now be doing some more questions from the topic Waves 1, equations that have been tested in the previous KCSE exam, and we are going to see whether we have been able to apply this equation, and also relating with the terms that we learned, the terms associated with waves in solution of various problems. So thank you. Continue going through the work for better understanding.